So let's most importantly remember that exam 1 is this week. So what does that mean for us? So most importantly, it's due Thursday at 11:59 p.m. That's the official due date. So there's no class Thursday. Use that time to work on the exam, hopefully. Now, a few people have reached out about schedule conflicts and work and all that. And so in order to sort of make it as fair as we can for everybody, so I'll post the exam to Canvas no later than 8 a.m. tomorrow. So I might do it earlier. So if you want to make sure you understand that it's up earlier, maybe I do it tonight. I don't know. It's going to depend on how busy I am. But if you want it, just make sure you have your sort of settings on Canvas so that anytime I upload something, you get notified via email or phone notification. As I've said before, and it'll be on the instructions, the exam has really one rule. And that is, you're not to talk about the problems to other humans, whether they're in the class, whether they're your engineer brother or sister. You can use the internet, you can use our notes and your books and whatever you want, but what you need to do is not talk to people about it. The most important thing that your grade is going to depend on is going to be how well do you write up your solutions. Are they legible, or do they make sense logically? Is your notation correct? Stuff like that. Now, the first exam is going to be very much a learning curve for that. Many of you will lose points for things like poor notation, and that's what we'll learn from. And then we'll fix it for the second test, hopefully. So if you have any issues with this exam as far as time issues, whether you got work or vacation, I don't know what all your situations are, please reach out to me. But I think I'm giving you a fair amount of time to do this. It's not going to take you 10 hours to do this test if you've been practicing. So, okay. Very good. When in doubt, show details. Okay. Does anybody have a question about the test? Any going once, going twice? All right. Well, hopefully, if you do have questions pop up, you'll let me know at your earliest convenience. Okay, so very good. Excuse me. So what's the test going to cover? Everybody likes to know this sort of question. Look, the questions that we're going to ask you are going to be questions that we covered. So if you have the textbook, what does it cover? It covers from the time you were born up through chapter 6 and 8. We didn't do chapter 7. I mean, we sort of did it, but we're not asking you questions directly from it. So what you need to understand is all the homework's fair game. Now, of course, I'm not going to ask you a question that you were asked in 7th grade, but the point is, if you can't do your 7th grade math, you're going to have a hard time doing your university level math. So I'm kind of being funny, but it's kind of reality as well. Everything you've learned in mathematics from the time you were born, how to count and do arithmetic and algebra and elementary geometry, that's all stuff that you should know. But we're going to ask you questions from chapters in this book, notably 6 and 8. Does anybody have a question, comment, concern? Okay, so that being said, I posted a homework for you guys. I want to say yesterday at some point. So I'm assuming there's questions because these are some challenging ones. And since Michelle, you are the squeaky wheel, you asked first. We'll go with yours first. So you asked about H, I think. So let's do some examples. So the first one we're going to talk about is this one. We want to integrate 1 divided by this creature. So what does my brain sort of go with here? So me, the trained brain, looks at this creature and I see a couple things stand out. The first thing that stands out to me is a square root. I know that square roots usually mean that there's going to be some difficulty here unless I can eliminate it. And in order to eliminate a square root, you need one of 2 things. You need, in the simplest case, usually, which you'd like is you would like to be able to set what's inside equal to some new variable and do a substitution. But that's not going to work here. However, the 81, which is 9 squared minus x squared, that suggests that a trig substitution could very much do the trick for us. So let me be very clear with what I mean here. So the expression 81 minus x squared suggests the trig substitution of setting x equal to the sine of theta, and that means dx would be cosine of theta d theta. Now, again, it might not be suggesting that to you because you're just the baby amateurs. You guys are supposed to be learning this stuff. So right now, you don't have the same perspective that I have when it comes to how we're going to do these integrals. So how do you get the same perspective I have? Well, you got to do practice. You got to gain experience. And there's no other sort of substitute for it than actually doing that. Okay, so we have our strategy, and let's go with it. So that's what I'm going to do. So let's go with it. So the way I like to do it is I like to put everything in here. So I'm going to replace x with sine. So when I do that, what's the integral become? Well, everywhere I saw an x, I need to replace it with a sine of theta. So this is sine to the 4th of theta. Then I have a square root of 81. Oh, hold on. Let's back up. I guess I should be more careful. I made an error. It should not be sine theta. The correct choice would be 9 sine. 9 sine. So if that's the case, if I choose 9 sine, then everything's going to work out. So if I go back to the next slide, This will be 9 to the power 4 out front. Sine to the 4th, 81 minus 81 sine squared. And then our dx was 9 cosine of theta d theta. So make sure you understand where that 1 over 9 to the 4th comes from. And then these 9s are going to have 1 less because the 9 over 9 to the 4th is 9 cubed. The sine to the 4th will stay the same for now. Inside the radical, using elementary trig, this is 81 cosine squared theta. Then, of course, upstairs, we're left with just 1. And so this is cosine theta d theta. Now, lots of things are going to cancel. I have a square root of 81 cosine squared, so let's be very careful here. This cosine is going to cancel with this one. And then the 81 in the square root becomes a 9. So now I'm back to 1 over 9 to the power 4. Integral of 1 over sine to the power 4 theta d theta.
Professor?
Yes.
Why did it go from 1 over 9 to the 3rd to 1 over 9 to the 4th?
Because what's the square root of 81?
9.
All right, so what's 9 times 9 cubed?
9 to the 4th.
There you go. Does that make sense?
Yes, it does now. Thank you.
Okay. Yeah, I mean, there's different ways you could move these constants around. I just did it that way. I don't know if that's the best way to think about it. Maybe your brain interpreted these constants differently. Are we good here? Does anybody have a question about this particular point? So, and by the way, we did all that work, and now we're at in an integral that doesn't look much easier, does it? So we have to think about how we might want to go about this problem, this sine to the power 4. And what's worse is this is 1 over sine to the power 4. Okay, so before we go any further, it's important that we understand, did we make errors? Did we not make errors? Do we need to sort of double check this thing? Where are we at? All right, so if we're confident that we have gotten here and honestly and have no errors, the question is, how do we integrate this now? So there's a couple ways you can do this. What I would probably do is I would probably rewrite this as 1 over 9 to the power 4. And this is 1 over the sine is cosecant, so I might write it like this. Now, once again, this is not an easy integral. In fact, you may have never done this particular integral. And if you Google it, it might have this complicated expression. So what you're saying is, well, how do I even derive this complicated expression? So the shortcut, as James pointed out 2 classes ago, well, aren't there tables of integrals? Absolutely, there's tables of integrals. So when you have if you look in the back of your book, what you'll recognize is this thing becomes 1 over 9 to the 4th. This is called sort of, I don't want to say cheating, but we're using a table. So this would be negative 1/3 cotangent of theta. And then this is times the cosecant squared of theta plus 2. And what I'm using here, and I'm not, and we're doing this just for the problem. This is using, how did I go from here to here? I'm using the table in the back of the book. So that is one way of doing this problem. Of course, you might immediately ask, well, if this were on the test, what would I do? Well, if this were on the test, I would be very clear on how I'd want you to handle it. I might tell you what the integral of cosecant to the 4th is. Or I might leave it up to you. I might say, okay, should you know this integral? Should you know how to evaluate it? It's a very complicated integral if you don't know the tricks. So what if you don't know the trick? How do you do it if you don't know the trick? Does anybody have a thought about this? See, the thing with an integral like this is if you don't use the sort of reduction formula, then you have to rely on having a very well, or you have to be very, very well versed in different trig identities. All right, so before we go any further, does anybody have a question or need clarified what I mean when I say that we're using a table of integral to go from the last 2 lines? I mean, notice I went from an integral sign to having no integral sign. Now, that doesn't mean this is the only way of doing it. There's other ways you can proceed. You might think about, one way you can go about it without using the table is you can go and use partial fractions. If you were to, well, okay, I don't want to get too far. Okay, let me slow down. I don't want to get too overwhelming here. But you might leave the sign, 1 over the sign in the denominator, and think about how you might be able to factor that creature. Any way you slice it, this is a challenging integral. And so I would be very fair if this were say a test question. I would be completely fair in how I graded it and how I expected you to write up the solution. So one way to do it is to use a trig identity, by the way, and break this into cosecant squared, and then you can use some Pythagorean identities. I don't know if it's the best use of our time to do that. I'm not saying we shouldn't, but another way you might proceed is you might use integration by parts. You might break the cosecant power 4 up and then do some parts. However, for this particular problem, I am okay with you using a table here at this particular point of the problem. Does that make sense? I guess I'll, you know, I don't know how clear I'm being. Maybe I'm being more unclear. I'm not sure. And if I'm being confusing, I apologize. But the point I'm trying to make is, and if this were a test question, I would be ultimately clear with this. I would be okay with saying that you're allowed to use, and I'll explain this again when we do another problem, which we're going to do. You're allowed to use the table from this point forward. Does that make sense? All right, so even with us using the table of integrals, or even if us Googling it, I mean, when I say table, I mean, you could use Wolfram if you wanted, or some software on the internet. Yeah. So, but we're not done. I mean, if you want to finish this problem, you need to go back to the original variable, right? So to finish, you need to go back to x. So how do you do that? Well, you draw your triangle. And what was our original substitution? Our substitution was x equals 9 sine of theta. So that means that this is x and this is 9. And so by the Pythagorean theorem, as you would guess, this is 81 minus x squared in the square root. And so if we write it out, our original integral, which I believe was this, we found it was 1 over 9 to the 4th. And then this was, the integral was negative 1/3 cotangent theta times cosecant squared of theta plus 2. And so now you have to figure out what all these creatures are. So what is, for example, the cotangent of theta? Well, the cotangent of theta is 1 over the tangent. So if you take the tangent, that's x over this. So this becomes and then what's the cosecant? Well, the cosecant is 1 over the sine. So the sine is, of course, x over 9. So 1 over that is 9 over x, but you're squaring it. So this is 9 over x. So 7 years later, we arrive at this. So it's negative 1 over, you know, what's 9 to the 4th? 9 to the 4th is 81 squared, right? Right, I don't know what 81 squared is, so I'll look it up. 65, 61. And then you have to multiply that by 3, because there's a 3 down there. So what is that, 19? 683. And then this is what? The cotangent is this. And then this is times the cosecant squared, which is 9 over x squared. So you can write this as 81 x squared, and then plus 2. Holy cow. And that's just assuming or hoping we didn't make any errors. But that is an ugly creature, to say the least. So think about what we just did there. Particularly what you really should be concerned about is that triangle and what I got in the pink and how I got it. That's the kind of stuff that you'll definitely have to do. I mean, this integral, this is a very long and challenging integral. You would imagine on a test I wouldn't give you something this sort of involved. I mean, I guess I shouldn't say I wouldn't, but I highly doubt it. Does anybody have a question about this? A comment, a concern, a prayer? Okay, so the question becomes, how did I know what to substitute in for x? So if we go back to the first step, I said this expression suggests that. So what we said 2 classes ago now is anytime you have a square minus x squared, that is a sort of a siren that should go off to suggest to you to use x equals something times sine. So it's this term, I have a square minus x squared. Anytime I see that, something squared minus x squared, I should think to try this. It will often work. Now, if this was 16 instead of 81, I would have used 4 sine. If it was 64, I would have used 8 sine. So again, if we sort of put that in here, so anytime you have a squared minus x squared, this suggests x equals a sine of theta. So again, this is the kind of stuff, there's so much going on, we often, it seems super overwhelming. This stuff is difficult. So, you know, if you look at this homework that we gave you, some of these integrals that use the trig substitution aren't that bad, but it's all relative, right? I mean, when I say that bad, compared to what? I mean, in general, these trig substitutions are long, complicated integrals. This one was particularly ugly. So, thankfully, it's 2020 and there's software that can help us with this. And but this is also a calculus class. So part of this class is for you to understand how to do these things, even though a calculator can do it for you. Just like, you know, we're not going to stop teaching 3rd graders how to multiply just because a calculator can multiply for them. So now, are we going to expect you to be able to do the same amount of integrals, or should we expect you to do them that we would maybe be interested in 20 years ago? No, because we have software to do it for us. That being said, you still should know how to do these things. Okay, does anybody have a question about this problem? And if you don't have a question about this one, are there other problems on here that you want to talk about? Feel free to scream and shout it out loud. So I'll give here's a good example of what I was talking about before. In the past, I have given question 3 on the exam. Now, if you've done problems 2 and 3 yet, you'll realize that in order to solve problem 3, you need this formula in problem 2. So what I'm asking you to do is verify that ugly formula, integral of secant cubed. But in the past, I've given problem 3 on the test, and I've actually said, solve problem 3, but here's the formula. I didn't ask you to actually do problem 2. I gave it to you. But in my opinion, every calculus student should at least once in their life suffer from deriving formula in problem 2. And if you get stuck, there's a Wikipedia page for that integral. That's how important it is. It shows up in all kinds of places. It's also fascinating that if you think about the parabola, and determining the length of a parabola is actually a very, very complicated thing. And that sort of goes against our intuition, because often, like with a parabola, we think of it as a simple function, and its derivative is extremely complicated. Excuse me, it's the formula to determine its length is extremely complicated, not its derivative. Does anybody have a question about any of the problems in 1 on homework? What is this, homework 4? What about problems 2 or 3? Problem 3 is an extremely important problem. I hope you all work it out, and if you can't, you ask questions about it. It's probably one of, if you can, and it's hard, don't get me wrong, figuring out problem 3, although it's in your textbook, so it's not that ridiculously hard to figure it out. But problems 2 and 3 are very important. I hope you work them out. And then problem 4 is is a volume problem that requires some, ingenuity. So let's look at problem 4, because we haven't done these creatures in a while. So it's a volume problem. So basically, the curve we're interested in is this. And this guy, if we restrict it between, we don't want x to be any bigger or any smaller than 0, and what's the other one? 4. So this guy is rotated about the x-axis. So if you draw a picture of this, I'm not going to be completely precise here, but the graph sort of looks like this. So it sort of comes down like, you go to Desmos and you can graph it. And what we're interested in is we're interested up till 4. So we take the curve and then the region underneath it down to the x-axis, and we rotate it, and we're going to get some sort of 3-dimensional solid. So if we sort of rotate this thing around, our solid's going to look something like this. And so if we look at this object, since it's rotated about the x-axis, one of the things that we'll notice, if we carefully draw it and sketch it, is that its cross sections are all circles. And so what that suggests to us is to use the disk method. And so that tells us that the volume then has a very simple formula. The volume is given by the integral from 0 to 4 of pi times the function squared. So it's this squared. And of course, this simplifies a bit because the square root and the square cancel one another out, and you're only left with this. All right, so now, how do we integrate this creature? Well, this is going to be very similar to the previous example. The difference is we're going to use a different substitution because we're going to have to employ a different identity. Notice this is not minus. It's not 9 minus x squared. It's 9 plus x squared. So if I remember my trig identities, the useful identity here is that 1 plus tangent squared equals secant squared. And so I'm going to use a tangent substitution. So if we go to the next page, and I'll give it, does anybody have a question about anything that's on here before we proceed? All right, so what I'm going to do is this is pi integral 0 to 4. And I'm going to do a substitution of the following, and I guess I should be very careful. I'm going to move my bounds for now, because we know that those have to change. So if I come over here, what's the substitution that I want? Well, the term that sticks out to me in the problem is this 9 plus x squared. So what does this suggest? So it suggests that x equals the tangent of theta times 3. And then that means dx is 3 secant squared theta, d theta. So if I do that in my problem, I'm going to come back to my bounds in a second, but what I end up having is 1 over, this is 9 plus 9 tangent squared theta. And my dx is times 3 secant squared theta d theta. Now the thing I must be careful with are my bounds. What are my bounds? Well, when x is 0, so let's write this out very clearly, because I think oftentimes as students we have a problem doing this. So when x is equal to 0, we have to solve 0 equals 3 tangent theta, and that implies that 0 is equal to the tangent, 0 equals tangent theta. And the way you think about that is you ask, what angle has a tangent of 0? And the answer is what? Well, the answer is theta equals 0. So this bound is actually going to be 0 again. Now what about the next guy? What about x equals 4? Well, now I have to solve 4 equals 3 tangent theta. And this is not so clear cut and clean. This tells me that theta has to be the arctan of 4/3. Yikes. So you might need to think about that for a second. Here we have the arctan of 4/3. So this is not a rational number. It's an irrational number. And so we can't write it any cleaner. We can approximate it, but we're going to have to leave it as is. So that's what we have up here. So this is the arctan. Yikes. It's hard to fill this creature in. This is the arctan of 4/3. Now, of course, some of you are going to say, that's ugly. Oh, my God. Well, okay, let's be honest. You think when you decide to build a skyscraper, you're going to be integrating from 0 to 6? Right? When you want to put a robot on Mars, do you think you're going to integrate from 0 to 7? No. I mean, you got to imagine that in the real world, things are not so clean as you'd like them to be. Now, then your next comment will be, well, this is just homework. And I will say, yes, it is. But if you read the homework, one of the big mistakes that many of you make is you'll say, well, you're only going to do the problems that I ask you to turn in. But if you carefully read the homework, I am telling you, you should be doing as many book problems as you can possibly do. It's the only way to learn this. And so I am under the assumption that you guys are doing that. And so when I give you a problem like this, it is my hope, because this is the only way you're going to learn it, is that you've actually done more practice than just one of these. It's that you've done the examples in the book and the examples in class. I mean, that's the only way to learn this stuff. You can't just do 10 problems and expect to understand it. It just doesn't work that way. Okay, so if we clean this up, and by the way, and I don't say that, I'm not trying to be mean and say that. I'm trying to be as brutally honest as I can. The only way to learn calculus is to spend an awful amount of time in doing it, which is even more disheartening because you usually mess everything up at first. So, all right. So what I notice is this 3 can come out, so I have 3 pi. And then my bounds, I still have 0 here, and then I have this god-awful arctan of 4/3. But the nice thing is this denominator just becomes 9 secant squared. That's a trig identity. And then here I have secant squared. And so look at this. Beautifully enough, the secant squareds go away. Well, that's exciting. That is super exciting. And since they go away, what you're really left with is I can pull that 1/9 out, and I'm left with pi over 3, the integral from 0 to the arctan, 4/3. And then what you're integrating is just 1d theta. And so when you integrate it, you get pi over 3 times the arctan, 4/3 minus 0, and that's your answer. Yikes. By the way, there was a you didn't have to do a trig substitution here if you remember some stuff from Calc 1, but it was worth the practice. So again, not by any means an easy problem. Not an easy problem. Does anybody have a question or a comment?
So I was wondering, after you got rid of the radical,
Yes.
and you were just left with the 1 over 9 plus x squared.
That's right, yes.
Before you did the trig substitution, could you have gone and done a partial fraction?
Oh, no,
route?
not a partial fractions, no, but it's even easier than that. Partial fractions wouldn't work because you can't factor 9 plus x squared.
Oh, that's true.
Right? But it's even easier than that. If you think about your Calc 1 knowledge, that's a simple arctan. So here's the alternative way. And I might as well just spell it out for you so you guys have something to compare it to. Once I'm at this point right here in the bottom right, this integral 0 to 4, 9 plus x over 2. If this was just 1 over 1 plus x squared, that's just an arctan, right? Remember your arctan formula for the integral. So an alternative solution is the following. I mean, they're really the same thing technically, but you're just going about it differently. So alternatively, you could recall that the integral of 1 over 1 plus x squared dx is just equal to the arctan of x. So you could have used that from the very beginning if you make the appropriate substitution. So let me spell it out for you. So then your volume, which was pi, right? Was it pi? Let me just make sure I don't mess it up. I think it was pi. Yeah, just pi times that integral. So if you have the integral from 0 to 4 of 1 over 9 plus x squared dx, you can just do a basic u substitution. So what you need to notice is if you factor out a 9, you get pi over 9, integral 0 to 4 of 1 over 1 plus. Now you could rewrite this as x over 3 quantity squared. So we actually would have done this in Calc 1, a similar problem. And then now, instead of doing a trig substitution, you can use the formula that I have written in blue above. And if you just set u equal to x over 3, then your du is 1/3 dx. So what does this integral become? If you plug that in, and you know, I don't want to go too slow. Uh-oh, we got crying babies. Okay, so bad news for the youngins. Wonder what happened. So when I replace my x's and dx's, this just becomes, when I replace dx with 3 du, I get pi over 3 integral 1 over 1 plus u squared du. And what are my new bounds? My bounds are now 0 to 4/3. And so this becomes pi over 3 arctan of u from 0 to 4/3. And then we get the same answer we had previously, pi over 3 arctan 4/3. So that would have been another way of getting the problem done. And you'll see that's the same thing we just got, 2 different ways. Now you could decide which method's easier.
If you chose to do it the first way, when we were computing the new bounds,
Yes.
could you use that arctan identity to simplify the upper bound?
Well, how are you going to simplify? What do you mean arctan identity?
Well, we came up with that upper bound for the integral from 0 to arctan 4/3.
Yeah.
Could you just plug the 4/3 into 1 over 1 plus x squared
No,
equals
no,
arctan?
no. That's not, be careful. Be very careful. That's not the identity. The identity is arctan is the integral of 1 over 1 plus x squared.
Oh, okay.
It's not an algebraic relationship. This is not an algebraic relationship up here. So what you're saying to do, Paul, and that would be bad news, is you're saying that you want to use this relationship. No. This relationship is not algebraic. There's an integral sign out front. So you can't just say if x is 4/3, you can't just plug 4/3 in both sides. That doesn't make any sense.
Got it.
Now, if it was, what's that?
Got it. I just missed the integral symbol in front of there for a second.
Yeah, that's good. That's why you ask. Here, let's clean that integral sign up so it doesn't look so misplaced. How about that? So if I put the integral sign like that, there you go. So what we're actually using is what you suggested. We use it correctly at this line right here. See this line where I have the integral from 0 to 4/3. When I go from here to here, so if I put this, if I go from this one to this one, that's when I'm using the correct way of what you suggested. Because it's a calculus relationship, which means we have to use what's called the fundamental theorem of calculus. Oh my God, there's just so much to remember and learn. Isn't this so daunting? Look, I can even use some weird word, daunting. Anybody have a question about this? Yeah, there's a lot happening, guys. There really is. Part of me feels bad, but then I remember I had to go through all this. So, you guys can do it. So, integrals that look like this are, we're not just making these up to give you headaches. These types of integrals arise in all kinds of physical settings. I mean, lots of settings, but particularly we showed you already when we're computing surface areas and we're computing lengths of curves, these integrals pop up. In physics, when you want to study things like electric charge and magnetic fields and electric fields, these kinds of integrals help us describe and quantify the behavior of things like electric and magnetic fields. So if you're going to be an engineer, you're going to get to learn all this stuff. Again, in another class. Questions? Comments? These types of integrals, I mean, I keep saying, I always like to give context for things. You want to talk about ballistics. You want to projectiles. How far will this missile have to travel? How far does my space shuttle have to travel? I mean, how far is a home run ball gun? I mean, if you want to do these calculations exactly, they require integrals of these types. Any questions about this? Any other questions on the homework? So we're not going to do any new material before the test. The test is just going to cover these types of integral, all these techniques, integration by parts, by substitution, trig, partial fractions, and then of course the applications, the areas, the volumes, and all that.
Can I ask about 1C?
You sure can, yeah. Let me pull it up because I don't remember what it is. Okay, do you have a specific question about it?
Yeah, I just wanted to make sure I was on the right track. So I started setting x equal to 3 sine theta.
That's correct, yep.
Okay, and then you end up with...
Let's look at it. Let's see if there's any subtleties or anything that sort of pop up. So if this is what, number 1C? So once again, the observation you make is the correct one, we think. I mean, there might be another way of doing it, but the x equals 3 sine theta looks like a good starting point. And so if we do that, upstairs you get 9 minus 9 sine squared. And then this is over 9 sine squared. And then, of course, you have a 3. We'll bring it out front. And then you have a cosine theta d theta. And what's nice is inside the square root, that just becomes 9 cosine squared theta. That's the Pythagorean theorem. Then I have this other 9, which I'm going to pull out. And then I'm left with a sine squared still down here. And then a cosine squared. Oh, excuse me. That's not a cosine squared. That's a cosine. Okay, so what happens? Upstairs, you get the 9 becomes a 3, so you end up getting just a 1 out front. And then the cosine squared, what you end up getting is cosine squared over sine squared. And if you want, you might think of this as sine over cosine is tangent, so this is the cotangent squared. So then the question might be, okay, how do I go from here? Where do I go from here? Because it's not entirely obvious what's the best way to proceed. Always. Now, that being said, there might be multiple ways that you can proceed. Some of them probably would not come to you unless someone stirs your imagination. So, did you get this far, Paul?
I messed up somewhere along the way.
Messed up. I mean, that's okay.
I'm missing the cosine after the fraction.
Okay, but even so, I mean, how do you integrate the cotangent? Is it easy? Is it not easy? These are the things that the more practice we have, the sort of the easier things become. Is it an easy one? Well, then you might say, okay, am I missing something? So it turns out this is one way to finish the problem, but again, I don't know how useful this is. So one way to do it is to not write the cotangent. So maybe you don't know how to integrate the cotangent, and that's fine. So let's think about it. Now, and by the way, it's not hard to look it up, but let's say you don't know it. So let's go back to this cosine squared over sine squared. Let's see if we can do some sort of simple or reasonable manipulation. So here's what I note. If I go to the next page, so I have cosine squared over sine squared, and I'm not quite sure what to do with this. So the first thing I'm going to do is just follow my nose. I'm going to write cosine as 1 minus sine squared. And the reason I want to do this is because if I do this, now I can write this as 1 over sine, which is cosecant squared, minus 1. Now this is good because I know how to integrate 1. And then the only thing is, do I remember how to integrate the cosecant squared? Well, that is actually a straightforward one if you paid attention in Calc 1, because the integral of cotangent is cosecant squared, which means this becomes minus the cotangent of theta minus theta plus c. So this is one way to proceed. Now, again, we're not done because we're in theta, and this is all super overwhelming because it seems like these problems have 47 pieces to them. And in a lot of ways, they do. So what was our original thing? Our original thing was x equals 3 sine theta. So if we draw that triangle, this is theta. You have this as x over 3, and then, of course, that means, excuse me, wrote that wrong. Then this is, of course, as you would expect, 9 minus x squared. And so what's the cotangent? The cotangent's 1 over the tangent, so the cotangent is, this becomes negative 9 minus x squared over x. And then what's theta? Well, theta is the inverse sine of x over 3. So that's the final answer to this creature, which again is a brutal problem. So there's something that needs to be repeated about these things, and I'm going to do it again. If you are in another class, then you would use software to do all these integrals. And even later in the semester, we will allow you to use software to compute these. But right now, you are part of the curriculum is requiring that you know how to do these by hand. So you should know how to do this. Even though they're tedious and scary and difficult. Does anybody have a question about this? So this is another one. It looks like it might be easy from the beginning, but then it becomes quite involved. Whew, fun times, huh? All right, does anybody, so what do you mean by as a calculator considered okay, James? I don't know what you mean by that. I mean, if I gave you this problem on a test, I expect to see all the calculation. I want to see the work. Now, I can't stop you from just copying it off of, you know, Symbolab or Wolfram, but I still expect you to write down the details of the calculation. Yeah, if you just tell me the integral and the answer on the test, you're not going to get full credit. So my hope is that you'll take the time to learn it. But I mean, I'm not going to stop you if you guys just copy down what you see. I mean, that's your choice, your personal choice. Because part of also what's important is that you understand what these integrals can tell us. So when I phrase these problems in an application setting, then you'd have to understand how that works too. So, you know, again, the details are important, specifically if I say so. And so on this test especially, I'm going to expect details. Now, whether you've done them on your own or you've gotten help from the internet, then I can't really tell. But that's just what it is, you know. You know, put it this way, in third grade, they're still going to ask you to multiply digit numbers together on a test, but after third grade, no one's going to expect you to do it by hand. You got a calculator, right? Same thing here. On this test, we expect to see you work out these integrals in detail. You know, when you're in physics class, they're probably just going to say use a table or use a calculator. So it's all about where you're, you know, what the goal is. All right. Any other questions about these problems? Going once, going twice. And if you guys don't have any other questions, I mean, I say go study and get ready for the test by tomorrow morning. If you do have questions, then ask. But I'm not going to hold you hostage. I know you guys are busy and in all kinds of predicaments with the whatever the heck we call this. It's insane. All right, well, listen, if you guys don't have any questions, I say thank you for joining the party. I will talk to you guys hopefully in the next day or so if you have questions. All right, thank you very much. Take care.